In this video, we will be looking at developing a UAV fuel simulation model within the Simulink environment. So if you watch my previous video on modeling a UAV in the OpenVSP environment, there I talk about extracting the aerodynamic data from a CAD model. So now that we have a CAD model, let's look at how can we simulate the fuel burn characteristics of a UAV. So in this video is going to serve as an introductory tutorial to Simulink, as well as a small application based project which will help you get started with your engineering assignments or any other projects relating to UAVs. So in a simulation model, we have a combination of different subsystems of the UAV. So you have the aerodynamic model, and you also have the propeller model, which generates the thrust for a given UAV, and then this propeller is connected to an engine. So the engine in this case study is a two-stroke IC engine, and we will be looking at using a specific fuel consumption map to map out the fuel burn over different flight conditions. And then we also look at how can we model the fuel burn based on a given fuel weight. So for our study, we are going to use a UAV with an empty weight of 15 kilograms and a fuel weight of again 15 kgs. So the total takeoff weight of the UAV is 30 kgs, and we also assume a wing area of 0.6 square meters. So when we look at a simulation model, initially it would look like a black box wherein you have a certain set of inputs and you want to extract some useful information out of the simulation model. So the first one is we input the altitude and the airspeed. So this simulation model deals with the cruise phase of the flight. So once we have the altitude and the airspeed defined, we can then compute what is the fuel that's being consumed by our model, and also what is the estimated endurance that we are able to get out of a particular design. So the data flow would occur to this block diagram that I've shown here below. So we start off with the aerodynamic model, and then once we get the lift and drag forces from the aerodynamic model, we then use that to model the characteristics of the propeller. And once we know the torque generated by the propeller, we can compute the specific fuel consumption value of the engine. So here is a reference UAV. So for this study, we have a fixed wing UAV, which is powered by a fixed pitch propeller, and this propeller is attached to a two-stroke IC engine. And this is the data flow as I have described before. So one thing what we're going to do in this study is that we are going to limit our simulation to the cruise phase of the UAV mission. So an important thing to understand here is that in cruise condition, you have an equilibrium of the aerodynamic forces. So essentially, when we are flying at a constant altitude and at a given airspeed, the cruise condition ensures that your lift is equal to the weight of the aircraft, and your thrust is sufficient to overcome the aerodynamic resistance on the UAV. This way, we know that we have an equilibrium of forces, and these are the fundamental equations which we'll be using to develop our simulation model. So coming to the aerodynamic model, on the left side we can see a representative UAV drag polar. So the drag polar is essentially the variation of the lift coefficient of the UAV with increase in drag coefficient. So this would give us important informations of what could be the reference cruise coefficient as well as the drag coefficient. Another important parameter that we can visualize here is also the lift to drag ratio. So we also know what is the best cruise condition to obtain maximum aerodynamic efficiency. Then on the right hand side, we have our lift and drag equations. So the lift and drag produced is a function of the air density, which is denoted by rho, the square of the airspeed denoted by v, the reference surface area, and the coefficients at the particular cruise phase. So to start off our simulation, we need to first generate an initialization script. So for this study, I have generated a file called initialize, and then I'm also input my reference aero data, and then I have an Excel file within which I have my drag polar data, which I will show you shortly. I have my Excel data sheet wherein I have already preloaded the required aerodynamic coefficients. So the first column has the lift coefficient, followed by the drag coefficient and the lift to drag ratio. So once I have this data, I will first import this data into the MATLAB environment, and this data is being exported as aero UAV matrix, and then I will subdivide these into their representative values. So once I have these values, I want to develop a polynomial equation which would model the drag polar characteristics. So to do that, I use the polyfit function, and I also specify the order of the polynomial, which is 2. So let me quickly show you the drag polar plot. So this is the variation of drag coefficient with lift coefficient. At the same time, you could also see how well the polynomial that I have generated would also try to map the same data. So here we see that our generated polynomial, which is of the second degree, has been good enough to capture the nonlinearity of our drag polar, and there is almost very small amount of error which is acceptable for our simulation. So once I have the polynomial generated, next I also input the propeller data. So for the propeller data, I start with the diameter of the propeller, which is a 19-inch propeller, which corresponds to 0.482 meters. And I've also imported the necessary values that are related with the propeller. Now to extract the propeller data, you can check out this site, which is UIUC propeller data. And this site contains a database of multiple propellers in their non-dimensional coefficients, and this becomes very useful when you are going to select propellers for your UAV based on their application. So the propeller that I have chosen for this study is the 19-inch propeller, and this 19-inch propeller, the representative characteristics are plotted on the left hand side. So we can see the variation of the thrust coefficient, the power coefficient, as well as the propeller efficiency. So when we look at these coefficients essentially model the thrust that the propeller can generate as well as the power. So we can again dimensionalize these non-dimensional coefficients by multiplying them with the reference density, the RPM of the propeller, and the diameter of the propeller. Another important term here is an advance ratio, which is a performance parameter that's related to the propeller. So you can compute the advance ratio as the airspeed of the UAV divided by the product of the RPM and the diameter of the propeller. So here I have imported the advance ratio values of our required propeller from the UIC database, and I've also exported the polynomials, which is the third order curve fitting for the variation of power coefficient with the advance ratio. Now that I have these propeller data installed, lastly I'm going to load the engine data. So the engine data that I have generated here is a scaled down sample engine which I've taken from a website where I can extract the variation of specific fuel consumption with a given RPM and torque. So this website has a representative value of a 4-stroke IC engine, and what I've done is I've scaled down these values to make it similar to a generic 2-stroke UAV engine. So this data, I'm currently loading this onto the MATLAB workspace, and I can also quickly generate a contour plot to visualize our engine performance map. So here is our generated contour, and when we are running our UAV simulation model, what we can essentially do is compute what is our specific fuel consumption value for a given torque and an RPM that is provided by the propeller. So now that we have defined all of the relevant parameters, I will now move into the Simulink environment. These Simulink files are also available in the link that I have posted below in the video. So you can go out to my GitHub page and download these files and try it out for yourself, and also carry out any other kind of studies on any kind of performance aspect that you like. So as defined before, we have 4 major blocks. So the first one is the aerodynamic block. Then we have the propeller block, followed by the engine block, and then the fuel burn model. So let us first look at some of the constants that we require here. So this constant here is the maximum takeoff weight of the UAV, which I have currently set it as 30 kgs. Another input is the wing area, followed by air density and airspeed. So if I have already defined my wing area in my initialization script, I can directly call the variables to the constant block here. So once I have my inputs, let's first look at the aerodynamic block. So for the aerodynamic block, we mainly looked at these 2 equations, which has to be now modeled in Simulink. So to model the lift coefficient, we essentially divide the weight by the density, the square of the velocity, and the reference surface area, and I also use a gain block to add the additional 0.5 multiplicative value. So once I have my lift coefficient, so I use these display scopes to visualize the values that the simulation produces. So this is a very easy debugging tool to understand what are the values that's being generated, and does it make sense that these values are actually generated by the Simulink model. So for the given CL, I also need to find my drag coefficient, and to do this we had previously discussed a second order polynomial, and that is what I have defined here within this block. So within here I have defined the coefficients that are a part of the drag polar, and with the help of these coefficients I can then compute the representative drag coefficient. Once I know the drag coefficient, I can then easily compute the drag force in newtons by multiplying the non-dimensional coefficient with the UAV operational parameters. So I have neatly packed all of these subcomponents within a subsystem, and I call this the aerodynamic block. So once I have the drag that's produced by the UAV in the cruise flight condition, next I need to compute the propeller torque, and the RPM. So that leads us to the propeller model. So within the propeller model, to compute the propeller characteristics, the first step to perform here is to compute the advance ratio from the drag of the UAV. Now to do this, I have all of the representative values and also loaded the advance ratio values from the UIUC database. So once I have these values, I generate a MATLAB function called compute advance ratio. Here I have defined the input arguments to these function, so which is namely the airspeed and the air density. So the first thing that I compute is the rotations per second. To do that, I can reorder this equation and compute the value of n. So once I have a value of n, I can then compute the thrust coefficient that's required by developing this polynomial equation. So once I have thrust coefficient, I can then generate the values of the thrust that the propeller produces by solving for the equation here, which is the first equation. And then once I have both the advance ratio, that is J2, and the thrust produced, I generate a polynomial function which shows me the relation between these two parameters. And this essentially lets me to compute the required advance ratio of the propeller to provide the required thrust to overcome the drag of the UAV. So once I have my advance ratio here, I will then compute my power coefficient, which is again defined as polynomial coefficients here. Then finally, I find the torque coefficient by dividing the power coefficient by 2 pi, and then again dimensionalizing the torque coefficient. So the output of the propeller model that's of importance is the torque that's produced by the propeller and also the RPM. So one thing to note here is that for our propeller calculations, the rotations value here is in rotations per second, but for our engine model we require rotations per minute. So we ensure that the correct conversion is done. Next, let us look at the engine block. So within the engine block, I have now fed in the propeller torque and the RPM, and I've also multiplied that by 60 to convert from rotations per second to rotations per minute. I have now defined another function block here. So what this function block does here is that it takes in the engine data and also the corresponding torque and the RPM that's produced by the propeller to compute a given SFC. Now this specific fuel consumption value that we get out after interpolation has this following units, that is kg per watt hour. Once I have the SFC, I will then use the SFC to model the fuel burn. So how do I model the fuel burn? So looking at the dimensions of SFC and the terms on the right hand side of this equation, if we multiply these two terms, we then get the rate of fuel burn, which is essentially kilograms per hour. So we multiply the SFC that is generated by the engine block into the drag produced by the UAV and the airspeed and the propeller efficiency, and this then gives us the amount of fuel burn. So once we have the fuel burn rate, we can then multiply this fuel burn rate with the simulation time to get an estimate of the quantity of the fuel that's being burned. So for this I use a clock block, and I also convert the seconds from the clock block to hour by dividing this value by 3600, which then gives me the flight time. So let me just quickly run this block. So now that I've successfully run this simulation, we can see some of these values in between the simulation. So here we see that for this particular operating condition, we have an advance ratio of 0.595, and which also corresponds to a torque of 3.756. Also, we know that the specific fuel consumption value, which is produced here, is 682 gram per kilowatt hour, which on converting it to our SI units would give us the corrected value. And then we also have the flight time, that is 5.56 hours with 15 kgs of fuel. And then finally we can also evaluate how the UAV loses its maximum takeoff weight as the fuel is being burnt. And we see that the simulation is run for a total time of 20,000 seconds, which roughly corresponds to 5.56 hours. So to update our takeoff weight, I have now connected the fuel burn value back to the UAV weight. So, and this subtraction block subtracts the value of the fuel burn from the initial weight. I also use a transport delay block here because at the start of the simulation we would encounter some kind of problems because we don't have the fuel burn value available. So that's a very quick run through of a fuel simulation model in Simulink. Feel free to comment below and also play around with the simulation model. I hope you learnt some good ways to develop a Simulink model, and if you like this video, please subscribe to my channel for more such informative content.